This is the most dangerous problem in mathematics, one that young mathematicians are warned not to waste their time on. Pick a number, any number. 7? Good choice. Okay, we're gonna apply two rules. If the number is odd, we multiply by 3 and add 1. So 3 times 7 is 21, plus 1 is 22. If the number is even, we divide by 2. So 22 divided by 2 is 11. Now we keep applying these two rules. 11 is odd, so we multiply by 3, 33, and add 1, 34. Even, divide by 2, 17. Odd. Multiply by 3, 51, add 1, 52. Even, divide by 2, 26. Still even. Divide by 2, 13. Odd. So we multiply by 3, 39, add 1, and that's 40, which is even. So we divide by 2, 20, divide by 2, 10, divide by 2, 5. Odd. Multiply by 3, 15, add 1, 16, divide by 2, that's 8, and then 4, 2, and 1. Now 1 is odd, so we multiply by 3 and add 1, which equals 4. But 4 goes to 2 goes to 1, so we're in a loop, and the lowest number is 1. Now the conjecture is this. Every positive integer, if you apply these rules, will eventually end up in the 4-2-1 loop. This is commonly called the Collatz conjecture after German mathematician Lothar Collatz, who may have come up with it in the 1930s. The numbers you get by applying 3x plus 1 are called hailstone numbers. They all fall down to 1, or at least we think they do. You can think of the numbers as representing the height above the ground in meters. So a number like 26 would start 26 meters above the ground. And if you apply 3x plus 1, it rises up as high as 40 meters, and in total it takes 10 steps to get to 1. So 10 is called its total stopping time. But take the very next number, 27, and it bounces around all over the place. In fact, it climbs all the way up to 9,232. As an altitude, that is higher than Mount Everest, before it too falls back to the ground. In total, it takes 111 steps for 27 to get down to 1 and end up in the 4-2-1 loop. Here is the sequence of a large number chosen at random. The graph peaks and then drops so low that you can't really see what's happening at this scale. But if you take the logarithm, you find this wiggly graph with a downward trend. It looks kind of like the stock market on a bad day. And this is no coincidence. Both are examples of geometric Brownian motion. That means if you take the log and remove the linear trend, the fluctuations are random. It's like flipping a coin each step. If the coin is heads, the line goes up. Tails, it goes down. 3x plus 1 is just like the random wiggles of the stock market. Over long enough periods, the stock market tends to trend upwards, while 3x plus 1 trends down. Another way to analyze 3x plus 1 is by looking at the leading digit of each number in a sequence. Here are the hailstone numbers starting with 3 as the seed. And we can count up how many numbers start with a 1, how many start with a 2, how many start with a 3, and so on to make a histogram. We can do the same thing for the sequence that starts with 4, that's a short one, and for the sequences that start with 5, 6, and 7. Again, for each sequence, we're just counting up how many numbers start with each digit, 1 through 9, and adding that to our histogram. If you keep doing this for more and more numbers, eventually the histogram settles into a stable pattern. For the first billion sequences, you'll find 1 is by far the most common leading digit. 30% of all numbers start with 1. Around 17.5% start with 2, 12% start with 3, and the frequency decreases for higher digits. Fewer than 5% of all the numbers start with 9. Now this pattern is not unique to 3x plus 1. It actually comes up everywhere, from the populations of countries to the value of companies, all the physical constants and the Fibonacci numbers, just to name a few. The distribution is known as Benford's law. And it is even used to detect fraud. If all the numbers on your income tax forms obey Benford's law, then, well, you're probably being honest. If not, you may be hiding something. In elections, Benford's law can be used to spot irregularities, though you have to apply it correctly. But Benford's law can't tell us whether all numbers will end up in the 4-2-1 loop or not. For that, we need a different sort of analysis. Now, at first glance, it seems strange that when you apply 3x plus 1, all numbers should end up at 1. But odd numbers are more than tripled, while even numbers are only cut in half. Therefore, it seems like every sequence on average should grow, not shrink. But here's the catch. Every time you multiply an odd number by 3 and then add 1, it will always become an even number. And that means the next step is to divide by 2. So odd numbers are not actually tripled by 3x plus 1, they're increased by a factor of about 3 over 2. I'm neglecting the plus 1 because it's insignificant for large numbers. And 3 halves is actually the most an odd number can grow in one step. Think of the path from one odd number in a sequence to the next odd number. After multiplying by 3 and adding 1, you have an even number. And 50% of the time, dividing by 2 brings you back to an odd number. But a quarter of the time, you can divide by 4 before you get to the next odd number. An eighth of the time, you can divide by 8 before getting to the next odd number. And a 16th of the time, you can divide by 16, and so on. If you take the geometric mean, you find, on average, to get from one odd number to the next one, you multiply by 3 over 4. Which is less than 1. So statistically speaking, 3x plus 1 sequences are more likely to shrink than grow. Take 341, for example. Multiply by 3 and add 1, you get 1024, which you can divide by 2, and then divide by 2 again, and again, and again, and again, 10 times in total until you're down to 1. One way to visualize these paths of numbers in 3x plus 1 is simply to show how each number connects to the next one in its sequence. This is called a directed graph. It looks like a tree, or a series of little streams that flow into each other. If the conjecture is true, it means that every single number is connected to this graph. Every tiny stream all the way out to infinity eventually flows into the massive river of 4, 2, 1. Some mathematicians have modified this visualization by rotating the graph at each number, anti-clockwise if it's an odd number, and clockwise if it's even. And then you end up with a structure that looks like a coral or seaweed. And by adjusting the degree of rotation for odd and even numbers, you can create these beautiful, organic-looking shapes. Now, there are two ways the conjecture could be false. There could be a number somewhere, some seed, that starts a sequence of numbers that grows to infinity. For whatever reason, it doesn't obey the same numerical gravity as all of the other numbers. Another possibility is there exists a sequence of numbers that forms a closed loop. All the numbers in this loop would be unconnected to the main graph. But thus far, no loop, or sequence that shoots off to infinity, has been found. And not for lack of trying. Mathematicians have tested by brute force every single number up to 2 to the 68. That's 295 quintillion, 147 quadrillion, 905 trillion, 179 billion, 352 million, 825,856 numbers. We know for certain that every single one of those numbers eventually comes back down to 1. We have tested nearly 300 quintillion numbers, and none of them disproves the conjecture. In fact, given this information, mathematicians calculate that any loop other than 421 must be at least 186 billion numbers long.